Hello, my name is Anke Hagen. Today I will derive the kinetic expression for an heterogeneously catalyzed reaction. Our example is A reacts with species B to AB with a certain reaction rate. And this is the parameter we would like to derive. Why is it important? If we know the kinetic expression for the reaction rate, we know how we can influence the reaction, for example, by selecting the right operating conditions such as temperature, pressure, partial pressures, also by selecting the right reactor concept in order to reach the maximum reaction rate towards the desired product. This reaction can be divided into individual reaction steps. For our example, we assume that species A comes from the gas phase. We then express the concentration as a partial pressure of A. It reaches the catalyst surface, where it adsorbs on an active site. The concentration of adsorbed species is expressed by theta A. There are different mechanisms. For our example, we assume that also species B comes from the gas phase. Concentration is again expressed by partial pressure. Species B is adsorbed as well as on an active site with a concentration of theta B. Then those adsorbed species react with each other to form the reaction product AB, which is desorbed. From these individual reactions, we have to determine the rate limiting step. That means the step that is the slowest and determining the overall reaction rate. We assume here that the surface reaction of the adsorbed species is the rate limiting step. We can then write the reaction rate equal to a reaction rate constant K times the adsorbed species A times adsorbed species B. So now we have an expression for the reaction rate. The problem is that concentration of adsorbed species are very difficult to determine experimentally. So the goal now is to find a correlation that only contains parameters that we can determine experimentally. In order to achieve that, we are considering additional correlations. As we have assumed that the surface reaction is the rate limiting step, that means as well that all the other steps are fast or in a thermodynamic equilibrium. For example, the step of A from the gas phase reacting with the surface side on the catalyst to give an adsorbed species A is then a fast reaction or in equilibrium, which is determined by the equilibrium constant Ka. Ka can then be written as the concentration of adsorbed species A, which is here on the right-hand side of the equation, divided by the partial pressure A, that means A coming from the gas phase, times the concentration of active sites. We can write the same for species B. B reacts with a surface site to give adsorbed species B, and as it is a fast reaction, it is in thermodynamic equilibrium and can be written as Kb equals adsorbed species B divided by partial pressure B times free surface sites. As we are looking to find a substitution for the concentration of adsorbed species, we just rearrange these two equations into theta or adsorbed species A is then equal to the equilibrium constant times partial pressure times free reaction sites. And the same for the adsorbed species B is then the equilibrium constant Kb times partial pressure B times free reaction sites. So now we can substitute these concentrations in the reaction rate equation. And we obtain the reaction rate is equal to the reaction rate constant, and then we substitute this expression, equilibrium constant times partial pressure times concentration of free sides times, now for B the same, equilibrium constant times partial pressure times free surface sides. So what we have achieved is we have substituted surface concentrations that are difficult to determine by partial pressures. Still, we have here this parameter, the concentration of free surface sides, that is very difficult to determine as well. So we need to find a substitution for these terms as well. We know that the total number of active sites on the catalyst, N, equals the number of free sites plus those sites that are occupied by species A plus those sites that are occupied by species B. So now we can use this expression. At first, we are again substituting the concentration of adsorbed surface species. So we use again for these concentrations the same expressions here. So we insert equilibrium constant times partial pressure times free sides plus, and for the B side we take the same for species B, equilibrium constant partial pressure times free sides. And then we simplify this equation and obtain number of surface size, total ones, is the concentration of free sides. We factor out the free sides and then obtain this expression. Sorry, KB, PB. Now, as the unknown term is the concentration of free sides, we rearrange the equation into this parameter. Concentration of free sides is then the total number of active sites divided by 1 plus equilibrium constant times partial pressure A plus equilibrium constant partial pressure species B. So now we can actually also substitute this term in the reaction rate equation. So that I will do over here. Then we arrive at the reaction rate is equal to reaction rate constant, equilibrium constant, partial pressure, species A, and so I'm going to this equation here. And for the concentration of the free surface sites, we take this new correlation, total sites divided by 1 plus equilibrium constant, partial pressure, species A, plus equilibrium constant, partial pressure, species B. And then we take the other half of the equation afterwards, which is KPPB, that's coming from over here, times, again, the concentration of free sites is the total number divided by 1 plus Ka partial pressure A plus Kb partial pressure B. So now we have achieved that we have an expression for the reaction rate R that is only dependent on partial pressures A and B, which we can determine experimentally. Now we are rearranging this equation to make it a bit more simple. So we can write in the numerator the reaction rate K, and we have 2 times the total number of catalyst sites, so means square. And then we can put these 2 terms in the numerator, means equilibrium constant partial pressure A times equilibrium constant partial pressure B. And in the denominator we have these 2 expressions, and that is 1 plus KAPA plus KBP. PB squared. So this is now our reaction rate expression. A bit easy. Some of the terms here are constants. For example, this one here. Sometimes you put that into a constant term, and then you see how the partial pressures PA and PB are affecting the reaction rate. You can then measure them, determine reaction rate, and see if you get the right correlation, the one that we have arrived at. If not, then you know we have made the wrong assumptions initially. So maybe the reaction is not that the adsorbed species react with each other. Maybe there is another reaction mechanism, and then you have to go back to your assumption and find the correct reaction mechanism. The one I sketched here, where you have two adsorbed species that react with each other, are, for example, the reaction of carbon monoxide reacting with oxygen to give carbon dioxide on a platinum catalyst. Here, both carbon monoxide and oxygen are adsorbed, giving CO2. Another example is the hydration of ethylene on copper catalysts to give ethane. This mechanism where the two species are adsorbed and react with each other is called Langmuir-Hinshelwood. There are other mechanisms that is, for example, the Ehley-Rydell mechanism, where you have a species A coming from the gas phase, adsorbing on the surface, and then reacting with B directly on the gas phase to give you product AB. In that case, we have, of course, a different expression for the reaction and for the reaction rate. So, for the example of a Langmuir-Hinshelwood reaction, we arrive at the reaction rate expression shown over here, with the shown dependencies of the partial pressures of the reacting species. And based on that, you can now determine what are the most optimum partial pressures. You can determine, when you measure the partial pressures and reaction rate at different temperatures, you can determine activation energies, you can determine the desired temperatures, the total pressures, and also select the reactor for this type of reaction. Thank you for following this example.